So yesterday we were talking about the model, okay, where we were looking at the school data and we were doing multi-level analysis on the school data where we were trying to understand. If I share my screen, uh, we were looking at this data. We had math as the predictor, as the predicted variable, or the dv, and we were having uh, individual SCS information. We were looking at the three level 2 variables, SES mean, Prof 4-year, and public as the variables. And let us go to our environment and let us resume from where we were uh, doing, or where we stopped yesterday. So the first thing that we have to do when we start our R is we set our working directory. Okay, so I go to that same uh, tab, session, set working directory, and choose directory. Okay, I have the folder on my desktop, so I go to that folder, multi-level, and I open it. So wherever you have set it, please set the working directory, and then we will load. So when we closed R, you should always save workspace, and now you will see there is a command in the same tab of session. You have load workspace. So everything that we would be doing, or we were doing yesterday, it would be saved, right? And uh, is it? I think I have not saved it, but anyways, I will show you. Yeah, so there is this. When we close, we should always save workspace. Okay, so you should save it, and you just save it in the multi-level folder. Okay, and when you go to session, you should say load workspace. So you will have load workspace, you will have that uh, file there, but I think I missed saving it anyway. So doesn't matter. If we have not saved it, we will open our R script. Okay, so let us open that school R script that I mailed you today. Okay, and we'll do it once again, and this time we will save it, and I will show you maybe next time how you can load the workspace. So now we will simply say library multi-level. Okay, this is, please note, this is the R script that I mailed all of you this morning. Okay, so I'm using the new, or the revised, and I will show you what are the changes that I have made, and we'll go over all the steps right from the beginning just to refresh, and then we will come to the random intercept and the random slope model. So line number 5 is where I am linking, because last time we had already installed the package. So every time you open R, you don't have to install the package. Now we can simply link the package. So I have directly run line number 5, and you see it has run, and it says library multi-level. Correct? Now, what we are saying is line number 7. I am reading my school data set. So the school data set has been read, 6,871 observations. If I click on school, you will see this data opens up, right? So this is the data set that we are going to use. Name schools just gives us the names of the variables that are there. Now, if you remember, yesterday we were saying null dot model, which is the first step, right? The step number one is we say null model, and what is the command? LME, the fixed effects, comma the random effects. So math is regressed on 1, which is the intercept, and random is equal to tilt 1, which is again just the intercept, and we are saying that intercept varies per school code for every school, right? It varies for every school. Data is equal to school. This is something that I told you that we will put this as an optimization control. You don't have to worry about it. Now you will see I have added one more command in the function. I have specified method is equal to maximum likelihood. Yesterday, I think there was a question. Kanika asked the question. Restricted maximum likelihood, as I said, cannot be used when we compare models. So we should if we are using or if we want to compare models, then maximum likelihood should be the estimation function. So I have rewritten the file, the complete R script, just to show you how right from the beginning we will also add this switch now every time we run a model, and that is method is equal to ml stands for maximum likelihood. Okay, so that is what I do now on line number
So,
10. Yes,
so just a question here. So maximum likelihood when we say here, so the system will then tell us between the two models which is a better model using the logics of the ML, right?
using the logic of
Maximum likelihood.
yes,
Because we have now said method ML.
and we said that how does it compare? It compares by calculating the difference of the deviance, which is minus
Multiplied by
2
minus 2.
minus 2 log
Yeah.
likelihood. Okay,
Yes.
and the
Okay, sir.
difference follows a chi-square distribution.
Sure, sir.
So
Yes, sir.
that distribution is followed when you are estimating it using the maximum likelihood.
Got
Okay,
it, sir.
so it
Thank
is
you.
not the logic of maximum likelihood, it is the difference which follows a chi-square distribution. Okay, difference of deviance of two models follows a chi-square distribution. That is the
Okay.
logic that it applies when it compares the two model, right?
Right, sir. Thank you.
Okay. Right, so we did the null model and then we display summary. So I'm just revising the steps that we had covered. We got this AIC, BIC, and log likelihood is this. Who will tell what is deviance? What is deviance? Deviance is minus 2 times log likelihood. So what will be the deviance? Let me open my calculator. The deviance is going to be minus 2 or 2 multiplied with minus 24437.91. So your deviance is going to be 48875.82. That is what the deviance is going to be. Let me make a note of this so that we can also check when we will be comparing. So let's say null dot model deviance is equal to minus 2 times minus 24437.91, which is equal to 48875.82. That is the deviance of the first model. Okay, then we got the random effects and we said standard deviation of, that is the standard sigma u0 is 3.256799, and sigma r is 8.15. And then we said the fixed effect, this is gamma 0, 0. It is significant. It is significantly different from 0. And then this is the distribution of the residuals, okay, Rij. Then we wrote variance covariance. So it gives us the sigma square u0 and sigma square r. So I said ICC dot null model, it is sigma square u0, that is 10.64223 divided by 10.64223 plus 66.5130. Okay, and that is what we get. Okay, and now you see it is slightly different. Why? Because yesterday this we had written for REML. So let us change this number. This now we are getting using the maximum likelihood. So there is a slight difference because we have changed the method of estimation. So let us just make this change. 60674 plus 66.5131. Okay, there is a slight difference. And now when I run this, I will get my ICC1, which is 13.74. That is what we were also getting. Okay, about the same. Then I told you another way of calculating ICC1 and ICC2 is using the ANOVA function. Okay, and you say ANOVA, the variable of our interest, and you just do
Sir,
one way ANOVA. And what is the factor? It is cool code. Yes, tell me,
sir,
Kali.
sorry to interrupt again, but which is the file that you're using today? Which is the script that you're using today? The one that you sent today or the one
Yes.
that we worked on yesterday?
No, we are
Okay.
using the script that I mailed today.
So with the additional commands or the multi-level R, sir?
No, it is school.r.
Okay, sorry, my bad. Thank you, sir.
It is school data, school.r.
Okay, sir, thank you.
Okay. And then we said ICC1, it comes out to be about the same, 13.77. Okay. And then you do ICC2, you get 0.723. Okay. Now we said, what is ICC2? That the group means differ significantly. That means the mean of math for group 1, group 2 up till group 419, they are significantly different from each other, and we said that our cutoff of ICC2 is it should be greater than 0.70. So our ICC2 is actually greater than. So we are again getting an evidence that there is significant difference across groups of our variable of interest. Then I told you that there is a third way. So there was a slight, you can say, error in writing that function. I had written capital G. So R is a case sensitive language. So now I have given the right function. So it is G mean rel, okay, group mean reliability. So you just run this command and you get grel dot dat, and then you say grel dat $ICC, so you get ICC1. Okay, and it is exactly the same as we had got 17.13 point or 0.1374677, and you see using the gmain rel also you get 0.1374677. And then you do, this is the command to compute ICC2. You simply say mean of mean reliability. Okay, so just do the mean and you get about the same 0.72. So this is the ICC2. So this is how you can again compute using the third way. So I have shown you ICC1 three ways: one, then ANOVA, and then using this function. You can report whichever is giving you the best result, the highest values. You can try it out and report it. Okay. Any questions? Anybody? All of you are getting these results? Anybody is not able to get it? Please tell me before I move on. Is this
So
okay?
I'm just curious about one thing, sir.
Yeah.
So this ICC2 value, is it uh, quite similar to what we get the F value when we are looking at the cluster analysis or LPA? Because in that we use it. Is there any kind of
No,
good?
it is not.
No. Okay.
It is not. I showed you the presentation yesterday. I
Yes,
showed
yes,
you
yes.
the
That I
formula.
remember, sir.
It
Yeah.
is, yeah, it is not. It is just telling us that the means are the within group variance is much
And
smaller than
then
the
the between.
between group.
Right, sir.
It
Right, sir.
is an
Okay.
index of that. Okay. Any other? All of you are getting these results? Anybody who is not? Okay. Now, the next thing that I had done was I showed you if we don't do multi-level modeling and we just do single level modeling and I regress math on one. Okay. So again, you see, I have added method is equal to ML. I have added this everywhere now so that our comparisons become realistic and meaningful. So null dot model dot 2 and then I have written ANOVA, and now when I compare these results, okay, you can see that the second model AIC and BIC are more than the first model or the null model AIC and BIC. Then the -2 log the log likelihood. So if we open our calculator again and do the same, let us compute our deviance once again. -24679.26. Okay, we get 49. So our null dot model dot 2, the deviance is equal to -2 times -24679.26, which is equal to 49358.52. Now if I calculate the difference, let us do that. 49358.52 minus what was the first deviance? 48, sorry, minus 48875.82. 48875.82. You get 482.7. Can everybody see? We are getting this result 482.7. Okay, this is something that is important for us. This is how it is calculating, and it varies, it follows a chi-square distribution. Now also let me tell you, how do you get this DF? You should ask, what does this DF mean? Okay, what does this DF mean here? Okay, DF is nothing but the number of parameters in the model, right? So let me open. If I write this simple equation, math I, okay, I am doing single level modeling. I don't do any multi-level. So I say is equal to beta 0 plus Ri. Right? This is my regression equation. This is this is of course writing the null model equations. So how many fixed effects? There is one fixed effect here, and you can say there is one random effect or one residual. So how many parameters are essentially to be calculated? The parameters are B0 and variance of Ri. So the number of parameters to be calculated are 2. If I do multi-level modeling, if I do multi-level modeling, what do I write? I wrote math ij is equal to, now I'm writing the direct equation, gamma 0 0 plus u 0 j plus r I j. Now how many terms? You have one fixed effect and there are two random effects. So how many parameters are there in the model? One gamma 0 0. Then you have variance of u0j to be computed and variance of rij to be computed. So how many parameters are 3? This is what it calls as df, number of parameters in the model. Number of parameters in the model. So you see the null model, the first model that we had run has a df of 3, and the second null dot model dot 1, right? Or the second null model that we had done, yeah, we had written, let me correct this, we had given it a name, null dot model dot 2 has a df of of 2, right? So if I go back to my output, you see it says null dot model has a df of 3 and null dot model dot 2 has df of 2. And so the difference is delta df. So now what we have found is that our delta deviance is equal to 482.7, delta df is equal to 1. So our hypothesis null is, this is, you can say, delta deviance is nothing but chi square, and our hypothesis was that chi square for its df is equal to 0 and chi square df is greater than 0. So what is it? For this chi-square at 1 degree of freedom, we have found that P is highly significant. So we reject our H naught, that chi-square is not 0. It is significantly different from 0. And therefore, what do we conclude? That the conclusion is, this leads us to that models are significantly
different.
significantly different. And which is a better model? Which is a more better model? Model
Null model.
having lower deviance, comma AIC, comma BIC are or is a better model. And which is that? Which is that? Our null dot model. And which is this null model? This is our multi-level model. And so what do we conclude from this complete analysis? What have we concluded? That doing multi-level modeling is better than doing single level modeling. And that is something that we are looking at. The second thing that the null dot model or is giving us, it helps us compute both ICC1 and ICC2. ICC1 we know is sigma square U0 whole divided by sigma square U0 plus sigma square R. We know from our analysis, we know sigma square U0 is nothing but 10.606. If I am not wrong, check your analysis. I think it is 10.606. Yes, and whole divided by 10.606 plus 66.51. How much it was? 5551. Right? That is what we are getting, and we say this is around 0.137, which means 13.7% variance of mean of math ij can be explained, or you can say attributed to level 2, is because of, can be explained because of schools, or can be attributed to level 2, which is schools. Right? That is what we are concluding from this analysis. Is this okay, everybody? Any questions here? Very important. I will not repeat it again. If Then from here on we will keep just calculating these indices. If you have any questions, please let us discuss it now. Okay, so let us go back to our R script now. This is what we have done. We have computed our null.model.2. We have compared, we have satisfied ourselves that doing multi-level modeling is important. Then what we had done, we had introduced the random intercept model, where we had brought in SES. Right, this is again something that we had done yesterday. We had brought in SES IJ, individual level predictor. We had not brought in any level 2 predictor for the random intercept, right? So it continues to be random is equal to 1, and it varies as per school code. There is only L1 predictor as of now, and you see I have added method is equal to ML at the end. Okay, this is what we ran, and now we get a summary. I will repeat it once more. Okay, the mathematical equations, just for your understanding once again, uh, and then we will move on. So our step 2 was random intercept. So what we have done now, we have said Yij is equal to beta 0j plus now beta 1j SES ij plus Rij. And let me replace y also now. Let us use directly our variable names. So math ij is equal to beta 0j, and this is our L1 equation. Then we wrote the L2 equations. We said beta 0j is gamma 00 plus u0j, and beta 1j is equal to gamma 10. These are our L2 equations. When we combine, what do we get? Math ij is equal to gamma 00 plus gamma 10 SES ij plus u0j plus Rij. So you have two random effects now, and you have two fixed effects. So what is our command? We say LME math is regressed on 1. So gamma 0, 0 is nothing but the coefficient of 1. So 1 plus SES. And then random, we say is equal to tilde 1 because U0J again is nothing but coefficient of 1 and it varies per school code. And then data is equal to school. Right? This is the command. Very simply, this is what we have written here. And we do this, we go to the summary. Okay, now what you see, you get your AIC fit indices, you get your standard deviations of U0J and Rij, and then you get the estimates and the test. So the now the gamma 00 is 57.59 and the t value and the p value is given. Then you have SES, it is this much, and is it significant? It is highly significant. And then you get the residuals. Okay, now if I do variance covariance of model 1, model dot 1, right, this is what we have now got. Initially you see we had 66.551 as the sigma square r. Now it has gone down to 62.803. Let us correct it because we have again, now there is a slight change because of the maximum likelihood estimation. So we can say the reduction in variance within schools is about 5.6%. So you can say this is pseudo r square at level 1. So how will we write it? We say you can say the pseudo r square. The pseudo r square of level 1 is given by 66.551 minus 62.803 whole divided by 66.551, and this is comes out to be 5.6% or 0.056. That means 5.6% variance at level 1 has been explained by SESij. Similarly, you get pseudo r square at level 2, which is nothing but 10 point, what was it, 606, 10.606. Let me just, yeah, 10.606 minus, what is it now? It is 3.442 whole divided by 10.606. This is our formula for pseudo r square at level 2. That means by bringing in, let us compute it using our R script. So let us write this as reduction in variance. Let me also edit the script and say this is pseudo r square at L1 and this is pseudo r square at L2. Okay, this is, let us correct it because these numbers are of the REMN. So this is 3.442 and this is 10.606. So this comes out to be 67.5. That just by bringing in L1 variable, even our L2 variance has gone down by 67.54%. What is the remaining now? What is the ICC1 remaining, or the proportion of variance that we can now still attribute to level 2 is 3.442 divided by 62.80. So now our ICC1 is 5.19. That means there is still 5.2% variance that is not been explained in the random intercept. And to do that, I want to bring in my L2 variables. And that is what I now write in model number 2. Okay. And what is going to be our model 2 equation? What am I trying to do now? Let us open a new whiteboard. What is it that we want to do now is diagrammatically, if you have to draw, you will say math ij and SES ij. Okay, now we have this. Now what we want to bring in? We want to bring in our three predictors: SES, mean, J, pro Fourier, J, and then public J. Let me write this clearly so that you don't confuse. This is pro Fourier college J. Now we want to test this month. So this is L1, this is L2. So what do we write? We say math ij is equal to the same equation beta 0j, beta 1j, SES ij plus Rij, and then we say beta 0j is equal to gamma 00, gamma 01, SES mean j, gamma 02, gamma 03, public j plus u0j, and beta 1j will continue to be constant because we are still modeling random intercept only. There is no random slope at the moment. So what do we get? We get math ij is equal to gamma 00 plus gamma 01 SES mean j plus gamma 02 pro Fourier college j, gamma 03 public j plus gamma 10 SES ij plus u0j plus Rij. These all make our how many? 1, 2, 3, 4, and 5. So we get 5 fixed effects and we have 2 random effects. So what will be the DF of the model? Anybody here?
7.
The DF is going to be 7.
7.
7. The number of parameters to be computed. What will be our command? We will say linear mixed model math is regressed on gamma 00 is nothing but coefficient of 1. So 1 plus SES mean plus pro Fourier college plus public plus SES, comma random is equal to tilde. U0j is nothing but coefficient of 1. So 1, and it varies as per school code, the grouping variable. And then data is equal to school. As simple as that. This is the command that we have to write. So we go to our, let us go to our R environment. This is what I have written on line number 41 now. Model.2 is, this is group level random intercept model. LME math is regressed on 1 plus SES mean plus 4-year college plus public. Random is equal to tilde 1 and it varies per school code. Data is equal to school, and then these are our two things that we will now always write. Doesn't make a difference, so you don't have to make any change here, even for your models. You will just have to change this part of the command. So now when we run this, and we do the summary, now you see we get the same. You get your fit indices. Now you get your, again, the random effects, standard deviation of U0j and Rij. Then you get your gamma 00, you get your gamma 10, that is the coefficient associated with L1 variable. So every change, every one standard deviation change, I was explaining this yesterday also, every one standard deviation change in SES will change the math score by 3.189 marks. That means students who come from better socioeconomic status, they tend to score higher on mathematics examination. SES mean J, okay, the coefficient is 2.47, and again it is highly significant. It means that students, keeping everything else same, students who are studying in richer schools or schools that cater to richer kids, they tend to score higher in mathematics by 2.47 marks. Then Pro 4-year college, it is 1.415, and that is also significant at P less than 0.01. And we can say that students who are studying in schools that are preparing students for university colleges, or where there is a higher percentage of students wanting to get into professional colleges, you have students scoring higher by 1.41 marks. And last, public schools, public private, that does not make any difference. Okay, whether you are studying in a public school or a private school, that does not make any difference. There is no significant effect after we have done this modeling, right? And now if we go to variance covariance, okay, this is our sigma square u0 2.33, and this is sigma square r. So what is the reduction in variance within schools? It is 66.551. Now what is our pseudo r square at level 1? Let us write it again. Pseudo r square at L1, which is equal to 66.551. Let us correct these numbers a little bit because we are estimating it with maximum likelihood now. So our pseudo r square is 5.9%. After bringing in all these predictors, we have been able to explain 5.9% variance. And pseudo r square at level 2, pseudo r square at L2 is 10 point, it was 10.606 minus, what is it now, 2.335 whole divided by 10.606. what do we get? 77.9% variance reduction we have been able to achieve. The remaining is still unexplained. Okay, that means there could be some other variables that may be at play, but we have been able to explain this much. Then ICC of model 1, ICC 1 now. This is how much variance is there now. 2.335 divided by 2.335 divided plus 62.622, right? Now only 3.5 or 3.6% variance you can say is still attributed to school level. Okay, so we started from, where did we start from? 13.8% variance, right? 13.77. If you look at our first ICC one, where is our first ICC one? 13.74 was the variance that we started with. From that, we have now gone down to 3.59. That means close to 10%, or close to 10, or you can say we can take the difference, 13.74 minus 3.59, this much whole divided by this much percentage we have been able to account for. Is this okay, everybody? Right? Any questions? Okay, now let's go to our randomly varying slope and intercept. Now this is where it starts to become interesting even further. Okay, it is already interesting. Now what are we doing? We are saying there is a random slope also. Okay, so what we had said, now we are coming to our final step, which is random slope and random intercept. Now what are we saying? We are saying math ij is equal to beta 0j plus beta 1j ses ij plus rij. We had written these equations yesterday also, but I am writing it again because we will derive the R command from this. Beta 0j is equal to gamma 00 plus you had gamma 01 SES mean j plus gamma 02 pro 4-year college j plus gamma 03 public j plus u0 j and beta 1j. Now what we are going to do, we are going to say it also varies. So now we have added this term u1j. When we combine, what happens to our equation now? Math ij is equal to gamma 00 gamma 01 ses mean j gamma 02 pro 4-year college j plus gamma 03 public j plus gamma 10 ses ij plus u0j. This is our first. Then second, u1j multiplied with ses ij plus rij. So these are our fixed effects. Again, 1 2 3 4 5 fixed effects. Now how many random effects? You have 3 random effects. What is the DF of the model? 5 plus 3 is equal to 8. What is the LME command? Now we will say the R command becomes math is regressed on 1 plus SES mean plus pro 4-year college plus public plus SES, comma, random is equal to tilde 1 plus, now there is, this is 1 and this is associated with SES. So we write 1 plus SES and it varies per school code, and data is equal to school. Is this okay? Very simple. We are saying 1 plus SES and it varies per school code, and that means both 1 also varies per school code, SES also varies per school code. That means there is going to be random intercept, and also the slope associated with SES is also going to randomly vary across schools. That is what we are saying when we write this command. Okay, so we go to our, yes,
So now here, just so I completely understand the I and J here. So J will be the school code
yes,
and I will be SES.
no, I, what is it that we were saying? I is ith individual
Right. Okay. 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 Right. Right. That's the case. Okay.
and J is the jth school,
Right, sir. Right. Okay.
right? That is what it means. That is what the IJ notation,
Sure.
SES,
Sure.
IJ means SES of ith student
Yes, sir.
studying in jth school.
Yes, sir. Thank you.
Yeah. Any other question? This is okay. So we go to our script, and you see now what we have written. If you go to line number 54, I have written math is regressed on 1 plus SES mean pro 4-year and public. These are our 5 fixed effects. Then random, we said there is randomness associated with 1 and there is randomness associated with SES. Now when you can write this also, or you can simply write SES, it will automatically mean that random intercept is also there. Okay, so 1 plus SES or SES. You see in my next I have simply written SES, but it means that there is random intercept, as well as it automatically means it would be 1 plus SES. So that is just a way of syntax, but 1 plus SES and data is equal to school. And then rest are the common things that we have written. Let us run this now and we do the summary. Let us look at the summary now. Our AIC, BIC and deviance, and now you see random effects. Now you start seeing that there are 3 random effects, which is associated with the intercept, associated with SES, and associated with the residual. Okay, and you see there is another which says correlation, and the correlation comes out to be minus 0.916. Now what is this correlation? So when we estimate this now, when you have both, let me write it here, when you have both u0j, let me use a different color, when you have u0j and u1j, So it predicts what it calls as a variance covariance matrix of L2 residuals. So it estimates not just, so it says sigma square u0, sigma square u1, and it also computes u0 u1. What is sigma u0 u1? It is nothing but covariance of u0 and u1. That is why now you see what are the parameters now in this model. Parameters are, here we had said the parameters are 5 fixed effects. So the parameters are 5 fixed effects plus 3 random effects. So we got sigma square u0, sigma square u1, and sigma square r. So 3 random effects now plus 1 covariance between u0 and u1. So the number of parameters are 8 plus 1. So the degree of freedom of this model comes out to be 9, because it also says I want to estimate not just sigma square u0, sigma square u1. I also want to know what is the correlation between these two residuals that I have now estimated. And that is why you see here in the output, it has not just reported the standard deviation of the 3 residuals, but it has also reported one correlation between the u0 and the u1. Okay, that is what we are seeing. And we now get our fixed effects, the same interpretation, everything remains the same. SES has an impact, SES mean has an impact, Prof Fourier has an impact, public does not have an impact. Okay, now if I do variance covariance of model 3, you will see sigma square u0 is 2.02, sigma square u1 is 1.44, and residual sigma square r is about 62.08. If we compute the previous model, model 2, which was random intercept with this random slope, if we do ANOVA line 57, you see, what does it say? Model 2, which was our random intercept model, the AIC was this much, BIC was this much, and log likelihood was this much. Now you see the parameters. Okay, the parameters are not 8, parameters are reported to be 9. In our random intercept, we had said there are 5 fixed effects plus 2 random effects. So there are 7 parameters or 7 degrees of freedom. So that is something. So you should not wonder why the degree of freedom is not coming out to be 8 but 9, because it has also computed this additional correlation here. Now if we compare, you see AIC has reduced, BIC has reduced, okay, and if we compare the two, our chi-square delta or delta deviance or our chi-square comes out to be 33.74. Degree of delta DF is 2, and this is highly significant. And which is a better model? A model having a lower AIC, BIC and deviance. So we are saying that not just randomly varying intercept, but randomly varying slope also is a good model. We should also model that there is a random slope. Okay, yes, Pavan.
Sir, how are we interpreting this slope intercept correlation? I'm
How are we? This one?
interpreting that. And yeah, yeah,
This
yeah.
one, it is nothing but you see it has obtained these two series. Pavan, it is
Yes, sir.
so when it estimated this model, it got a U0J series and a
Right,
U1J series. These are
right.
how many entries will it get? Can you guess how many entries in this series?
For J is like the number of clusters, and
Number of
for
clusters, very good. So how many
and
entries would be there? In this
that
case,
I
it
think we
will
have
it will be 1 to
four,
419,
right, sir.
right? So what
Yeah,
is U0J capturing? U0J is capturing what is after accounting for all this. What is the difference between beta 0J and the overall gamma 00, right? So this is
right, sir.
U0J and you have estimated U1J also.
Right.
So what is this sigma U0 U1? It is nothing but covariance of U0J and U1J. That's it.
So the basically the sign of covariance, like I mean,
Yes, do
does
they
that also imply
covary or
something?
not? Do they covary
Okay,
or not? So what is
right.
it that we are saying here? That the correlation is very high. Correlation C, it varies from -1 to +1, right? So
Right.
it is close to 1, but it is negative. That means what? That intercept variance and slope variance are moving in opposite direction between schools.
Okay,
Okay,
okay, sir.
but
Understood. Yeah.
you don't have to interpret it. It is just, but if you want to interpret, you can say that the deviation in the intercept and the deviation in the slope is very much correlated, but they are 180-degree opposite. They are opposite, varying in opposite direction, right?
Okay, sir.
That means for school one, you may have a deviation, positive deviation from the overall mean, and the slope is actually having a negative deviation from the overall mean. That is all that we are saying, but it is the software is estimating it. We typically don't interpret this. We say, okay, this is something that has been reported. That's it.
So,
But
sir, just to add on to that, so there could be a scenario where let's say the 50% of our schools are having the positive slope for maths marks and SES, and let's say 50% of the school has the negative slope.
negative
So,
slope, yes.
let's say, so in that case, that correlation could be like near to zero, right?
No, no, it is not. It is not for. It is not for one slope. You see, what is correlation? What is correlation? It is degree of association.
Right.
What you just, the example you said was 50% are plus, 50% are negative. That is what you said, right? For U1J
Yes, sir.
slope. But that does not matter at all. We are computing correlation with another series.
Okay, okay, sir. Yeah.
So this could be plus, but correlation will depend on what is the corresponding value of this
Oh, yeah, yeah, with the school, yeah.
with the U0.
Yeah, yeah.
You are talking about slope 50% plus and 50%
Mm.
negative, but that has nothing to do with correlation. The correlation is what is happening in another series with which I want to check the degree of association,
Yeah, yeah. Understood, sir.
right? So
Yes,
50% plus minus has no impact at all unless and until you know what is happening in U0J.
usual.
Are you
Yes,
getting it?
understood.
Yeah?
Yes, sir, yes, sir.
Hmm?
Yes, clearly.
Yeah.
Thank you, sir.
Okay, any other question? So this is what we write, right? Okay, and then we have tested the model and we have got this. And now comes the last part. Now that we know that we should model a random slope, I want to bring in level 2 predictors also for random slope. So what is going to be my model? I'm going to create a model like this. I am going to say now that I have SES IJ. How will you draw it in your papers or whatever you are doing research? Okay, this is my L1 level. Now at L2, I have SES mean J. It has a direct impact. So this arrow is telling me, random intercept, and I am saying it also moderates, and this is now telling me random slope. So it moderates this relationship. Similarly, I have pro 4-year college J. Let me use another color. This is telling me random intercept, and this arrow is telling me random slope. That means pro 4-year can also predict the variation in the slope. And then you have the third variable, public J. Let me use a third color. I say this is my random intercept, and this is my random slope. This is what we are trying to do. This is the conceptual diagram. This is the conceptual diagram. What will be the mathematical equation now? You say math ij is equal to beta 0j plus beta 1j SESij. There is no change in the L1 equation. This is our L1 equation. Now beta 0j is equal to gamma 00 gamma 01 SES mean j gamma 02 pro 4-year college j gamma 03 public j plus u0 j and beta 1 j. Now I want to bring in level 2 predictors for my slope also. So I write gamma 10 plus gamma 11 SES mean j plus gamma 12 pro 4-year college j plus gamma 13 public j plus u1 j. These are my L2 equations. When I combining, we get math ij is equal to gamma 00 plus gamma 01 SES mean j gamma 02 pro 4-year college j plus gamma 03 public j plus we get gamma 10 SES ij plus gamma 11 SES ij multiplied with SES mean j plus gamma 12 SES ij multiplied with pro 4-year college j plus gamma 13 SES ij multiplied with public j plus u0j plus u1j multiplied with SESij plus Rij. How many random effects? 3 random effects. How many fixed effects? 1, 2, 3, 4, 5, 6, 7, 8. You get 8 fixed effects. What is the degree of freedom? 8 plus 3 plus 1, which is covariance. Remember, one covariance will be estimated between u0 and u1j. So you have 8 fixed effects, 3 random effects plus sigma u0 u1. So now your degree of freedom of this model is going to be 12, and we will see that. What is going to be our LME equation now? What should be our syntax that we will write in our math regressed on 1 plus SES mean plus pro 4-year college plus public plus SES plus SES multiplied with SES mean plus SES multiplied with pro 4-year college plus SES multiplied with public. Just like we used to write do moderation in regression where we introduce the interaction term, that is exactly what we have done. We have introduced 3 interaction terms in our regression equation now. And we are also modeling the random is equal to tilde 1 plus SES per school code, and data is equal to school. That's it. This is the command that we are going to feed into the software in order to analyze what we are doing. So I have shown you how to draw this kind of a diagram, okay, then how to formulate the mathematical equation, and eventually how to actually analyze it using a statistical software. So let us now go to our R environment, and we are now saying randomly varying slope and intercept model.4. What am I saying now? Math is regressed on. You see, I have not written S1. It is automatically understood. So you write 1 plus, okay, you write 1 plus, or you don't write, it will automatically introduce intercept. Okay, this is just for your clarification. So 1 plus SES mean plus 4-year plus public, and you see I have now written SES colon. Okay, so you write SES colon or you write SES star, both are the same, doesn't matter. Okay, then SES pro 4-year college, you write colon or you write star, doesn't matter. Okay, and SES colon public, I am changing it to star again, doesn't matter, you leave it at colon, that is also fine. And you see random is equal to tilde, I have not written 1, but it will automatically understand that this is 1 plus SES. Okay, it will automatically understand that there will be random intercept. Okay, yes, it is. Yes, Yasmin, it you when you have a moderator, we will always do it is the software by default, it takes random intercept as well as random slope. So that is what this is showing, that you write 1 here or you don't write it, it always models that there would be random which is also right, because not just slopes may vary, you may also want to test whether the intercepts are varying. So it is always a good idea to do 1 plus SES. And then data is equal to school, and then rest are the same options that we have written. Okay, this is our command. Let us run this now, model 4, and we have got the summary. Okay, everybody, you have got it. Yes, I will come to that, Yasmin. When we have a mediating, is the same. You will do multiple regressions and then do it. So I'll talk about that. Maybe let me finish this first. So we have got our AIC, BIC, and deviance. Then we have got the residuals. We have got the sigma U0. We have got sigma U1, and we have got sigma R. Now we have got the fixed effects. You see, it is this regression that it has run. So you see SES, it continues to be significant. SES mean continues to be significant. Pro Fourier continues to be significant at p less than 0.01. Public was not significant. It is still not significant. Now you see the first interaction term is not significant. That means SES mean does not moderate. Does not moderate. Then pro Fourier, it does not moderate again. Okay, but now you see public comes out to be as a moderator. So you see the interaction SES multiplied with public. Now the interaction term of SES and public moderates, and it is a negatively moderating. That means for public you may see a slower rise in math score as compared to other schools. So public schools, the difference is that the rate of change, because it is a negative, so it negatively moderates the slope. That means the rate of change for a public school is smaller than for an other school. So in public schools also you may have rise in math score as socioeconomic status increases, but the rate of change may be smaller because we are now getting a negative coefficient. So if I go back to my model, what is this analysis telling me? This model is telling me that if I have to change my diagram, what will it be like? Based on what we are getting, we are now getting this kind of a model. You get SES mean, you have only a direct effect. There is no moderating effect. Then you have pro Fourier, you have only a direct effect. There is no moderating effect. And then you have public, you have, actually there is no direct effect. For public, there is actually an moderation effect. Okay, that means there is a, this is a conceptual diagram. Statistically, what are we saying? Statistically we are saying that, again let us draw it, SES to math, then you have SES mean, then you have pro Fourier college, then you have public, and you have SES multiplied with public. This path comes out to be significant. This is significant. Okay, this path is actually not significant. So I'm putting a red cross. This path from public, direct path from public to math, comes out to be not significant. However, this interaction term, we are seeing there is a significant effect, right? So this is your gamma 1 0, this is your gamma 0 1, this is your gamma 0, 2, and this is your gamma, whatever we said, gamma 1, 3, associated with public. This is moderating the path from SES to math, and that is the result that we are seeing. So you will have to draw these diagrams as well. Okay, you can draw these, and once you get these coefficients you can write it. So I check this now. I compared this with our previous model where we did not have any interaction terms. Okay, model 3 did not have any interaction term. You see it comes out to be significant. So this model is significantly different, and you see the degrees of freedom, it is 12, not 11. 8 plus 3 plus 1. So degree of freedom is 12. The previous model had degrees of freedom. Which is a better model? Which has lower AIC, which has lower BIC, okay, and the deviance is also different. Now you see, this is also an interesting case. You are getting AIC is lower, and but BIC has increased, okay, but we are seeing deviance is also lower. So we will consider that model if you are not getting consistent result. We are seeing BIC has increased, AIC has decreased. So in such cases where AIC, BIC show you different divergent results, go by what the deviance statistic is telling, and we are seeing that the deviance has reduced, okay, and it is also significant. So we will consider model 4 as a better model. And the last model now, here model dot 4a, you see model dot 4a, what I have done is I have removed all the non-significant interaction terms. So there were two non-significant interaction terms, SES multiplied with SES mean and SES multiplied with Prof Fourier. So I have removed those and retained only the significant, I have retained only the significant interaction term. Okay, because the other two terms are anyways not significant. So now if I run this command 65 and then I show you the summary, you will see what I am getting here is you have SES significant, you have SES mean significant, you have Prof Fourier significant, and you have SES public, SES multiplied with public, that term is also significant. Okay, and is this different from our previous model? It is not really different. You see 4 and model 4a, we just wanted to check, we just dropped. So you remove those non-significant terms or you retain them, both are fine. So you could have worked with model 4 or model 4a, that is absolutely fine. Okay, so this ends, this is what we wanted to do, okay, and we have been able to test this. Now let me take a pause and see if you have any questions. Anybody, you want to just take a look at what we have done so far? Any questions anybody has?
So we can also add like other control variables, for example. I
Yes,
mean, in the
yes,
model, like for
yes,
example, the
yes,
gender. We right.
absolutely. So you just change, you just write female here.
It's just the addition in the level one, but we are not checking the impact on gender. We are only checking the impact on
Yeah, yeah.
SES.
So you want to control, essentially, what is a control? Anyways, it's a variable that you introduce in your regression equation. So you introduce all the variables, whatever variables you want to include.
Sure.
Is that fine? Okay, so now we have got our final results. Now what I do is I want to uh, predict or plot the interaction. So it is very easy in R. You see, now we will look at what these variables are. So I am working with model.4a. So what are the variables? SES mean, Prof 4-year, and SES into public. Now let me, so whenever you have moderation, right? Let me, okay. Now, whenever you have a moderation, so what is it that we are saying? That there was a relationship between SES and math, and this is moderated by public variable. So when you have moderation, okay, I'm sure you are aware of this. We also plot a interaction. So we say that this is for public is equal to 0 because we have got a negative coefficient, and we will draw this is for public is equal to 1. What is this graph showing? That as SES increases, math increases, but the slope is smaller for public. That is, when public is equal to 1, the gradient of the line is weaker or smaller as compared to, because we have got the SES into public coefficient. What is it we have got? Minus 0.85. Okay, it's a negative. Had it been positive, what you should have expected, if it was positive, positive 0.85, you should have expected a graph like this, SES and then math. You should have expected a graph like this. This is public is equal to 0, public is equal to 0. You should have expected that if public takes value 1, then the slope should be positive, but it is not the case. The case in our situation is minus, negative. So this is called as negative moderation. This is called as positive, right? When you have a positive moderating coefficient, positive coefficient for the interaction term, the gradient of the line increases. When you have a negative interaction term coefficient, the gradient of the line reduces when the variable takes a higher value, right? This is what the case is. So we want to plot it. Now you should also remember that this is a multivariate equation, math ij, where you have some intercept plus you have gamma 01 SES mean plus you have gamma 02 pro Fourier and you have gamma 10 SES and you have gamma 11 SES into public. So we are interested in changing the values of SES and public, but there are other two values also, other two variables also, right? So we will hold these at their mean values. Okay, ceteris paribus. Remember, when we do multivariate regression, what do we say? Ceteris paribus. That means holding everything else constant. Okay, if I change SES by 1 unit, what will happen to the line? If I change public by 1 unit or change it from 0 to 1, what will happen to? So I need to hold others at some value. Now you can hold it at 0, you can hold it at, but a good thing is you hold it at their mean values. Okay, that is what, why I am telling you this, because this is what I'm going to do when I am going to plot my moderation graph. Now you see I have created, I am saying plotting the interaction, line number 70, plotting the interaction. What is the mean of the school and mean of the school SES and standard deviation, right? So let us report that. So this is mean is 0.032 and standard deviation is 0.781. So I compute two values, because to plot any line you need two values. So I have said mean minus 1 SD. In moderation, you are familiar that we choose 2 points, mean minus 1 SD and mean plus 1 SD. So if I run this, I get two values, minus 0.749 and plus 0.813. And for the others, SES mean and Pro Fourier, I report their mean value. So the mean is 0.032 and for Pro Fourier, the value is 0.8688. So I create a new data frame. Okay, I say temporary data and I call it as 419 because I will use this for plotting it for specific school. You can also plot this graph for specific schools, or you can plot it for overall data. I will show you. So it creates, because you also have to give it a school code. That is what it is saying. So data frame, I create a data frame. SES, what are the four values? First I say negative, negative, and then positive, positive. And public, okay, which is our moderator, I toggle it. I toggle it between 0, 1, 0, 1. SES mean, I am holding it at its mean value. Pro Fourier, which is another equation in my line, I am holding at its mean value, 0.869. And then I write school code, you see, I say 419, 419, 419, 419. So that means in this, I am going to say use this school code. Now this multi-level package has a very useful command. It says predict. And what is the model you use? Model.4a. Okay, using these coefficients that we had got, using all these coefficients that you have got. Okay, what it is saying, use this model coefficients, use this as the data and predict the math, and it says level is equal to 1. If I say level is equal to 1, it says predict it for this specific school 419. If I say 0, then it says predict it for the overall data. Okay, ignore this school code, use the overall gamma values. Otherwise, you add the U0j and the U1j to the slopes actually. Okay, so if you are doing your research, you can simply do level is equal to 0. I just wanted to demonstrate that you can also predict it for specific schools. Okay, you can change this to any number, you can change it to 1, you can change it to 2, but keep it constant for the entire data frame. So now when I run this, I get the math values. Okay, and I can also report, I can show you what are the math values. You see, it has predicted these four values. Similarly, I create another data frame where I give school code, but I say predict and keep level is equal to 0. Level is equal to 0 means ignore the school code and use the overall gamma values, of this, and then compute. Okay, So I run this and it has, again I can show you these values. There are again 4 values computed, and then I plot for overall. Okay, it says with this data frame do an interaction plot. SES is the X variable, public is the moderator variable, and math is the Y variable. So what happens is you get this plot. Now can you see you have got this plot? This is what we expected. Because there is a negative interaction coefficient, we expected that for public is equal to 0, we will have a steeper line as compared to public is equal to 1, right? Then I can also do the interaction plot for this specific school 419. I run this and you will see the lines are slightly different. Okay, actually let me just write one command. It says pair is equal to mf row 1 comma 2. Just a minute, I will write a command. Let me search that. Yes, this is the command. I just searched it on the net. So the command is, okay, I will paste it in the chat so you can all just copy it. Okay, now if I do this, what it does is it breaks this plotting chart into 2 columns, 1 row, 2 columns. Now if I plot, it will show you side by side. You see what we have got now? We have got this chart. So the left side was for overall, and this is for school number 419. So you can see, let me do this again. Let's clear it so that we are clear. This is for overall. So the first is for overall and the second is for the specific school. Yes. So overall, you see there is a slight change in the slopes. This is slightly narrow. This is slightly wider. But in your research, in your papers, you can just plot it for overall. You don't need to do it for specific school. You can say, okay, this is how it varies in our data. This is the impact of, this is the impact of the moderation that we are getting. Is this okay? This is called as plotting the interaction. If I have time towards the end, I will show you how you can do it in Excel also. It is very simple. We can create this chart exactly the same in Excel also. Okay, so I will show you on the last day if we get time. Otherwise, for now, you will just have to key in your values, whatever variables are there. Okay, key in their values, hold everything at a constant, at some constant. Okay, and hold every other variable at some constant, and then hold your variables, okay, which you want to toggle them, and you will get your values. Okay, any question, anybody? It is about 6:42. We can take a break now, and when we come back, we'll do this using SPSS, this example, and we'll look at another example in uh, another example also. But we'll first learn how to do everything that we have done in SPSS also, right? Any question? If not, let us take a break and we will come back at 5 o'clock. Let's take a 15-minute break and we'll come back at 5 o'clock IST, India Standard Time.